Okay, so we're going to start with part A of activity 22, which explores the properties and nomenclature of coordination compounds. So to explore the properties by looking at coordination compound formulas, we are going to fill out the table here. And so we're going to look at letter A and fill out the table for this one together so that we make sure that we know what we're doing. So the first thing we want to fill out is the complex ion. So ion means that it has a charge. So we want to make sure whatever we fill out here has a charge with it. So we should know that the complex ion is found in brackets in our coordination compound, which I've boxed here. So that is our complex ion, but again, it's an ion. We need to write the charge. So to figure out the charge, we look and see there's 3 chloride counter ions. That means our bracketed species, which there's one of, has to have a +3 with it. So that's why I'm going to write whatever's in the brackets here, and then the charge in this case is 3+. It tells us what the geometry is, in this case octahedral. So we want to list whatever ligand or ligands there are in this complex ion. In this case, there's only ammonia. There's 6 of them, but there's the only type of ligand we have is ammonia. The counter ion is outside of the brackets, and in this case, it's chloride. So there's 3 of them, but our counter ion is chloride. Coordination number, CN, stands for coordination number. This is the number of bonds to the central metal cation in our complex ion. So cobalt's in the middle. We have 6 ammonias. Ammonia is monodentate, meaning it just bonds once each. So we have a coordination number of 6. OX, the little 2 stars tell us, we look down here, OX is the oxidation number on the central metal. So looking at our complex ion, we see it has a 3+ charge overall. Ammonia is neutral, which means cobalt should be a 3+. And then charge, the 3 stars or asterisks down here say charge is the charge on the complex ion. Well, we already have that, right? 3+, so we're just going to write it here. So you're going to fill out the form for the rest of these. I do want to mention a couple things. F, I'm actually going to change. All right, I'm going to change. Before I change it, there's a little notation here, this little pound sign that's giving us a note that it's a neutral coordination compound with no complex ion or counter ion. I'm going to change this one, but this still holds. There's no, it's just a neutral substance. So here is the new one, platinum, and then ethylene diamine, and then 2 chlorides. All right, the whole thing is neutral. Okay, so this still applies. So since that still applies, there's no complex ion, so put a line through that. There's no counter ion, put a line through that one. And so put a line for this. There's no charge, there's no complex ion, so we can't really put a charge on the complex ion. I mean, technically the charge overall is 0, but since it asks for the charge on the complex ion, we're going to put a line through that one. Okay, so like I said, you're going to fill out the rest of this, and then once you do that, you're going to keep watching the video, and I'm going to show you some models of a few of these. And so you will investigate the models in the video for B, D, F, and H. Okay, and then you're going to need to draw these 4 structures on the sheet that I post in Canvas and turn that sheet in with your activity 22 report. Okay, it's an extra page. Be sure in all your diagrams that you're drawing to show the 3-dimensional nature of it. So you want to use wedges and dashes to indicate when something's coming out of the paper, those are the wedges, and into the paper, which are the dashes. Okay, so you want to make sure you indicate that for those 3-dimensional structures. Okay, so you'll have activity 22 plus this extra sheet where you're going to draw the 4 structures, B, D, F, and H. So I'll show you those on the video. You might want to pause the video when I show the still images of these so you can draw them on this extra sheet that you need to print out from Canvas. This is for B, the complex ion in B. This black piece represents a chloride ion. It has 4 lone pairs on it. So it's the ligand. It's going to donate a pair of electrons represented by this green piece to make the bond with the metal cation in the center. And overall, there is 6 chloride ligands Each of those donate a lone pair to make a bond with the metal ligand in the center. So this is our model for B, the complex ion in B. And it's an octahedral shape. We can see that there are 6, 1, 2, 3, 4, 5, 6 ligands to the central metal cation. Here is a still picture of the complex ion. The yellow arrow points to the platinum cation in the center, and the black arrow points to one of the chloride ligands. Moving on to the complex ion in D, here's the ammonia molecule with a lone pair, which is that bare peg at the top. And that is going to form the bond to the central metal cation. It's going to donate both those electrons to make the bond. And so I'm going to put the green piece on that lone pair and then build the complex ion model. So here it is. The black is the zinc ion in the middle with the 1, 2, 3, 4 ammonia ligands, and the overall shape is tetrahedral, as you can see here. Zinc has 4 ammonia ligands in the tetrahedral geometry. So here is a picture of it. The black arrow is pointing to the zinc, and the yellow arrow is pointing to one of the ammonia ligands. We're now going to look at F. This is the ethylene diamine ligand. There's a nitrogen, carbon, carbon, and then another nitrogen. It's a bidentate ligand. So it is going to attach twice to the central metal cation. I'm now attaching it. The lone pairs from nitrogen make the bond to the platinum that's in the middle. And so the yellow is the platinum, and then we have our 2 chloride ligands, as well as the one ethylene diamine, which is bidentate, attaching twice. So overall, we have a square planar geometry, right? So it's all in one plane, and this is our coordination compound in F. So here's a still figure. The yellow arrow is pointing to the platinum ion that's in the center. The black arrow is pointing to ethylene diamine, which is a bidentate ligand. It binds twice to the platinum ion. And the red arrow is pointing to one of the chloride ligands. There are 2 overall, and this is a square planar geometry. So here is chloride for H, and one of its lone pairs will form the bond to the copper ion that's in the middle. And there's 2 of them, so 2 bonds to the copper ion, and it's a linear shape. Here's a still picture for the complex ion in H. The black arrow points to the copper ion in the center, and the red arrow points to one of the chloride ligands. There are 2 ligands, and it's a linear shape. In part B, we will be examining isomers of coordination compounds and complex ions. First, you will investigate coordination isomers. You will just need to fill out the table for the 2 coordination compounds listed, write their names, and then be specific as you describe the difference between the 2 compounds. Now we're going to explore linkage isomers by using the nitrite ion as a ligand. We have a sigma bond and a pi bond between N and O on the left, and just a sigma bond between N and O on the right. So this is one of the resonance forms. You should draw both resonance forms in your lab activity. So now I'm going to go ahead and build the complex ion. We have 5 ammonia ligands, and then I'm going to attach the nitrite ligand through the nitrogen. So the nitrogen lone pair will form the bond with the cobalt cation in the center. But I also can attach it through the lone pair on the single bonded oxygen. So these 2 models I've shown you are linkage isomers. So here is a still picture with the nitrogen attached to the central metal cation, and that is called the Nitro Isomer. Feel free to pause this video so you can draw the structure in your lab activity. Be sure to use the dashes and the wedges to indicate the ligands that are coming out of the paper and into the paper to represent the 3-dimensional nature of the octahedral shape. You may write the ammonia molecules just as NH3. You don't have to show the NH bonds in any of these drawings. And then here's a still picture of the Nitro Isomer, and that is the oxygen attached to the central metal cation. Again, feel free to pause the video so you can draw the structure in your lab activity. Now we will investigate geometric isomers. We will start with the octahedral shape, where we have 2 chloride ligands represented with the red and 4 ammonia ligands. So this is the trans case, where we have the 2 chlorides opposite each other. Now I'm going to switch it up to the cis case, where we have now the 2 chlorides right next to each other or adjacent to each other, which is the cis case. So these are geometric isomers that we can have for the octahedral shape. So we will now look at some still images of both the trans and the cis isomers. Here is a picture of the trans case for our octahedral geometry. The 2 chloride ligands are directly across from each other, 180 degrees apart. And then the other 4 ligands are the ammonia ligands. Please feel free to pause the video to draw this structure. Now we will look at the cis case, where the 2 chloride ligands are adjacent to each other. They're right next to each other, or they're 90 degrees apart. So this is the cis case for our octahedral geometry. Again, feel free to pause the video to draw this structure in your lab activity. Now we will look at square planar that has trans and cis geometries. This is the trans case, where the 2 of the same ions are directly across from each other. Here is the cis case, where they are right next to each other. So the 2 ammonias right next to each other, the 2 chlorides right next to each other. So here is a still picture of the trans case. Again, the 2 chlorides across from each other, 180 degrees apart. And in this example, the 2 ammonia ligands are directly across from each other as well. And in our cis case, we have the 2 chlorides right next to each other and the 2 ammonias right next to each other. So this is our square planar cis. We will investigate some more geometric isomers called Fac and Mer. So this is the octahedral geometry, and we have 3 of one type of ligand that are at the vertices of one triangular face. So the 3 chlorides are at the vertices of one triangular face, as well as the 3 ammonias are at the vertices of one triangular face. And this is called the Fac isomer. So to make the Mer isomer, the 3 of the same ligand make a T shape here. So if we look at those 3 chlorides, they make a T. Or we look at the 3 ammonias in this case, and that makes a T, and this is called the Mer isomer. So here's a still image of the Fac isomer. Again, the 3 of the same type of ligand, the chlorides or the ammonias in this example, are at the vertices of the triangular face. Be sure to draw your wedges and dashes to indicate the 3-dimensional nature of this structure. Here's a still picture of the Mer isomer. The 3 of the same type of ligands form a T shape. So you can see those 3 red chlorides forming a T. The 3 ammonias also form a T. Now we will be looking at optical isomers. In this part, we are going to build some complex ions that contain the ethylene diamine ligand, the structure of which is seen on the screen. We used this ligand earlier in one of the models, and I actually built the whole ethylene diamine ligand to attach. Here, though, to keep things simpler so we can focus on the optical isomers, I'm just going to use the flexible white piece to represent an ethylene diamine ligand that is bidentate and bonds twice, as you can see in the model. And we are going to start with the cis form of this complex ion. So you can see that we have the ethylene diamines next to each other and the chloride ions next to each other. So it's the cis conformation. So now we want to look at the mirror image. So this is the mirror image of that model. And so I'm going to lay it down so we can see that it's the mirror image. So if the dashed line represents the mirror, these two models are mirror images of each other. So closest to the mirror, I have an ethylene diamine going back on each model. And then I have the ethylene diamine going out towards us. And then furthest from the mirror, I have that chloride, right? So these are mirror images of each other. So now I want to see if they're the same molecule. Can I superimpose these? So I flip it around so I can line up the chlorides, which are now lined up, but the ethylene diamines are not. This one's coming out at us, whereas in the other model, it's going back away from us. This ethylene diamine ligand is going back, and this one's coming out. They're going in different directions. I cannot superimpose them. They are non-superimposable mirror images. They are different structures. So here's a still image of the complex ion and its mirror image. So now here is the trans isomer of the same complex ion. We can see it's trans. The two chlorides are across from each other. The two ethylene diamines are across from each other. And so I can build the mirror image of this. So the dashed line is the mirror. And we can see that it's definitely the mirror image. Closest to the mirror, we have the ethylene diamine, right? And away from the mirror, we have the ethylene diamine. So those are mirror images. And so now, can I superimpose those? I can. Those lie right on top of each other. So it's the same structure. There's no difference. So here is a still photo of the trans isomer and its mirror image. This completes the models for activity 22. So now you can complete the activity. Don't forget to print out the supplemental page in Canvas and fill that page out as well.